isotopes are just atoms of the same element with different masses because they have different number of neutrons. Now let's take the carbon atom for example. Now the standard carbon atom, it has 6 protons, but there is actually 3 isotopes of carbon. One with carbon mass of 12. By the way, the top number here represents the mass, the atomic mass. Atomic mass. And this number as well. This is the atomic mass of those elements. And as we covered in an earlier video, the atomic mass it has 2 components. It has neutrons and protons. Now, if we establish the protons stay same, then the difference in mass could only be accounted for by difference in the number of neutrons. So, for example, carbon 12, it has 6 neutrons. 6 neutrons. I'm going to change the color of the pen right now just to illustrate. And carbon 13, it has 7 neutrons because you could just subtract the number of protons from the atomic mass to find the number of neutrons. So this one has 7 neutrons. And the last one, carbon 14, with an atomic mass of 14, has 8 neutrons. Now, which one do we take though? Which one do we use to measure the official mass, or what is known as the weighted average mass? So it's a weighted average. So whichever is more abundant is going to have more influence on the official weight listed in the periodic table. For example, for carbon, the official mass is 12.01. Now that's calculated, as you can tell, it's closer to the mass of the C12 isotope than it is to C14 and C13 isotopes. Why is that? Because C12 makes up 99% of all carbon. Found in nature. That is called natural abundance, carbon found in nature, right? So the percentage with which it is found in nature for a specific isotope is called the natural abundance. So we've established that the carbon 12 isotope has a natural abundance of 99%. Now, that obviously means the official mass of carbon, the official weighted mass of carbon, is going to be closer to 12 than it would be to 13 or 14, which only make up about 0.01. Pardon me, 0.01 decimal form, and then about 1% of all carbon. So it's going to have more weight when making the calculation. Now, the equation for finding the official mass, called the atomic mass, it goes something like the mass of one isotope times the natural abundance, and then you add all that up. So it's going to be, for example, for the carbon one, it's going to be the mass of C12 times natural abundance of C12. Others too. So mass of 13C times natural abundance of 13C, etc. And then you add the last isotopes. So let's do a question like that with magnesium. So the question reads, magnesium has 3 naturally occurring isotopes, Mg24, whose mass 24 AMU, and a natural abundance of 79%, Mj25, whose a mass of 25 AMU and a natural abundance of 10, and Mj26, whose mass 26 AMU and a natural abundance of 11%. So if you're going to find the weighted average or the atomic mass of magnesium, we need to add all the present isotopes and in a weighted average atomic mass. So for the first one, we're going to do the mass of it. So Mj24, which has a mass of 24. So the mass is always going to be written with the isotope. So 24 AMU, and it has an abundance of 0.79%. Now 79%, which is 79 over 100. That's what a percent means. We're going to write it in decimal form, which will make it equal to 0.79. All right. So let's add those in a vertical form so you guys can see all the work I put in. And the mass of Mj25 is going to be 25 AMU. I'm going to write it in a separate color. Twenty-five AMU, and if we do that thing where we convert them to decimals, so it's going to 10% in decimal form will be about 0.1, and you could also add the last one, 26. Mj26 will have a mass of 26 AMUs and a natural abundance of about 0.11, as the question states. Now, if we put on these values in our calculators, we're going to get 24 times 0.79 is going to be equal to 18.96. 25 times 0.1, multiplying by 0.1 is like dividing by 10, so it will be 2.5. And 26 times 0.11, that is going to be 26 times 0.11 is going to be 2.86. Now, if we add those all together, paying attention to significant figures, the answer would be 24.3 atomic mass units. 24.3. Atomic mass units. 24.3 atomic mass units. So that's going to be equal to 24.3 atomic mass units for magnesium, which is very, let's search up what the mass of magnesium is going to be. Which is, I think, would be very close to the official listed weight for magnesium. So magnesium has an atomic mass unit of 24.305 daltons. By the way, the U you see right here, on this U, it is the same as AMU, which is atomic mass unit, and then that U would be daltons. That's what it represents, which is the same as AMU. So I hope you found this video helpful. It is it covers a lot of the important stuff in elements, what makes elements elements, such as isotopes and their natural abundance. As well as how to find. We did a simple question right here. If you guys have any other questions, please let me know. Oh, before you go, I have another one. So if you're given an element such as Cr 52 24, 52 being the mass, and this being the atomic number, find all the other subparticles. I'll let you guys try that for a minute by yourselves. Pause the video and see how you guys understand the topics we've been discussing so far. But the best way to do this would be 52 is a mass, right? And 24, just from that, that's the atomic number. So the atomic number, as we already discussed, atomic number is equal to number of protons. So then the number of protons is equal to 24. Since it's a neutral atom, that means the charge is balanced. So protons are positively charged, electrons are negatively charged, and for it to be neutral, they have to be equal in number. Therefore, electrons are 24 as well. Now, the neutrons, number of neutrons, is going to be the atomic mass minus atomic number. If you guys want to know the reason behind the equation, that's because the atomic mass is made by a combination of the protons and neutrons, and the atomic number is just the number of protons. So obviously, if you subtract the number from the mass, you're going to get the number of neutrons. So 52 minus 24 is going to give you the answer to be 28 neutrons. And that's how you could use atomic mass and atomic number to figure out the number of neutrons, and how to use the given isotopes and their natural abundance to figure out what the atomic mass is. Figure out what they are. The only constant in atoms actually is the proton. The number of protons always stays the same for all atoms of one element. Always constant. That's why the proton is used to identify the atom via the atomic number, because it's just always constant. So if you're given the atomic number of an atom, you could always know what element it is. For example, if you know there's 2 protons, then that's a helium. But can you do the same with neutrons or electrons? No, because the number of electrons or neutrons for an atom, for 2 atoms of the same element, could be different. Electrons could be lost or gained, resulting in change of charge. There could be a change of charge because of that. Meaning, if you gain electrons, gain of them could result in becoming more negative. And if you lose them, like metals do, then you become positive. as an atom. Now, neutrons, if there is a variance in the number of neutrons, then that results in difference in mass between atoms with the same element. So they could be atoms with the same element but have difference in mass because they have different amounts of neutrons. Now, what do we call the signs? We call those isotopes. Now, isotopes they're officially defined as atoms of the same element that have different number of neutrons, and that results in difference in mass as well. Difference in mass. Sorry for the abbreviations. I like them. I like to use them because I'm a lazy writer. But anyway, so